Hi, this video was put in here because of the comments, the great comments we got from the Vortrix Algebra number 2, where we discussed, what do we call it, geometric algebra. So we're going to do a side-by-side comparison of all three vector algebras and show you proof that a vector product must result in a matrix and nothing but a matrix. Okay, and then the final conclusion to this will be that any vector algebra that does not produce a matrix as a result of a vector multiply is not what I will use going forward. Okay, because I know a lot of my Patreon folks are saying, well, you're kind of throwing away geometric algebra without really giving it a chance. I'm like, maybe so. But you got to realize I have limited time and I need to work with the tool I have the most confidence in. Okay, well, we'll discuss more of this later. I'm getting too much into the body of this right now. Okay, I just said that. So here are all the three different products. This is the legacy vector product, which results in a scalar and a vector. This is the geometric product, which results in a scalar and what they call a bivector, which I believe is a structure of two vectors. And then you have the Vortrix algebra, which really only produces a matrix, but that matrix can be separated into cross and dot components. But we rarely ever use this in Vortrix algebra. We always just stay with the product. We don't go crazy separating it like the other guys do. So let me give you a little background on anticommutative operators. And this is the definition. We're going to use the exterior algebra. We're going to start with that. We're going to explain that one. This is from Wikipedia, exterior algebra. Like the cross product, the exterior product is anticommutative, meaning that this, okay, if I take two vectors, u and an exterior product with v, then that's going to equal the negative of vu. In other words, if I swap the two vectors, the exterior product is negative if they're not swapped. And this is true for all vectors u and v. All vectors. But unlike the cross product, exterior product is associative. I really don't care about that right now. That's not really important here. So in other words, what they're saying is, if I'm going to use a and b instead of u and v. So the exterior product of a and b is equal to the negative of b exterior product a. But what happens if I substitute b with a, so that we have the exterior product of a, so that's equal to the negative. So the only possible solution for this, now this says for all vectors. So I should be able to substitute b with a in this equation here. Okay, all vectors. So the only solution to the exterior product of like structures is 0. Okay, so and that is also true for legacy algebra. The cross product of parallel vectors or like vectors is 0. And that's same for Vortrix algebra. The Vortrix dot product for like vectors comes out to 0. So this is consistent between all three geometries, all three algebras. Okay, so now if we're using our unit vectors, because remember, this is going back to the discussion of the pseudoscalar. In the pseudoscalar, we use unit direction vector in x and unit direction vector in y. And so if we take the cross product of the unit direction x and y, we get 1. If we take and we swap them, we get negative 1. Okay, that's consistent for legacy and Vortrix. It supposedly is consistent with exterior product, but I don't really know. You get a bivector, you don't get a scalar, which, okay, I don't know what a bivector is, but it doesn't matter because this is their definition. This is all we need. It's all I need is this. This is their definition. That's all I need to disprove them. You don't need to know anything more than that. Oh, there is somebody that says, well, when you get to higher levels or k spaces or whatever, this kind of oscillates, but that's not relevant because all they use for proving the pseudoscalar is this basic definition here. They don't go into the higher orders. That's beyond. That's like a generation beyond this. This is just the basic deriving the pseudoscalar. And this is the definition that's in vogue there. So the dot product is also consistent among the three algebras. If I take the dot product of like vectors or like constructs, it doesn't really actually really matter. These could be scalars too. Okay, I'm going to get the magnitude square as a scalar. So the dot product of like objects is positive with the magnitude equal to the vector squared. Now, if we go back and use our unit vectors here, these unit only have one, but because these are orthogonal, the dot product of orthogonal vectors is 0. So the dot product is a measure of how same the things are. Okay? How same they are. Where the cross product and these guys is a measure of how perpendicular they are. Okay? So if they're not perpendicular, if they're the same, then these all come out to 0. If these are the same for the dot product, it'll come out to the magnitude squared. If their magnitudes are 1, it comes out to 1 because 1 times 1 is 1, obviously. But if they're perpendicular, you get 0. The dot product of perpendicular vectors is 0. So let's go back to the pseudoscalar. They say, back in geometric algebra, and this will be the last time, this video is the last time we're going to talk about geometric algebra, that their pseudoscalar I is equal to the unit direction in vector in x. And we're talking about one dimension here. They do it for all dimensions. That's fine. Doesn't matter. You just proved one dimension, you disproved all dimensions. Is the exterior product with y. Okay. But let's do this. Okay, let's not put this in. Because what they do is they do a lot of stuff where they allow the operator in the product to swap around. In other words, you could use either operator depending on what's going on. So let's get rid of the operator and just call it like this. And we're going to do this for all three algebras. And it makes sense. Okay, so now what we do is now we're going to square both sides because that's supposed to, they need this to come out -1 for them to have truly derived the pseudoscalar. And we're going to do this for each algebra. Okay, let's start with geometric algebra step 1. So we substitute xy, but let's do this. Let's take the xy inside the parenthesis and substitute the geometric function. And this is what we get. We get the dot plus the exterior product of x and y. Okay, well, we know these two guys are orthogonal, right? Since they're orthogonal, the dot product of orthogonal vectors is 0, so we can cross this out. And this is why they always show this as using the exterior product. But now we've got to take the square of the exterior product. Okay, let's do that. And let's substitute that back into the geometric product because this is essentially a product of this times this. Okay, and so when we substitute that, we're going to get the dot product of this plus the exterior product of this. Okay, so what did we say before? Well, we said that the exterior product of two like constructs has got to be 0. So this is 0. Okay, and then over here, the dot product of two like construct is a positive value that is equal to the magnitude squared. But because all the magnitudes are 1, the answer comes out to just +1. It does not equal -1. Okay, now I can take this here and run down all the permutations. And this has to come out 1. If this comes out 1, the only answer for this is going to be, and if this comes out 1 and you desire the answer -1, then this has to equal this has to equal -2. Okay, because this does come out to 1. So if you're looking for the answer -1, this has to come out to be -2. I'm sorry, but no matter how many times you multiply -1 together, no matter how many times you multiply 1 together, you're never going to get a negative number. You're certainly not going to get -2, because these are all magnitude 1s. So the only answer here has to be 0. And even if we took the exterior product and changed the order in which you multiply all these, they all still come out to 0. Which kind of proves their associativity for exterior product. This is not true for Vortrix or legacy algebra. So let's go back, let's go to legacy algebra. Okay, we're going to do the same thing. Here's our xy squared. We're going to substitute the dot product and the cross product. Okay, again, the dot product of orthogonal vectors is 0, which leaves a cross product squared. Okay, and this is just copied what we had before. Okay, now we have this. We're going to do this now. So now we have the dot product of this times this, and the cross product of this times this. Well, the cross product produces a normal vector. So these are two parallel vectors. Again, this comes out to 0. This comes out to 1. The answer is 1. Still does not equal -1, but we didn't expect that to happen for legacy algebra. But it's interesting because this is consistent with a geometric algebra. It does not come out to -1. Vortrix algebra, step 1. We put the Vortrix algebra dot product and Vortrix algebra cross product. Again, the dot product of orthogonal vectors comes out to be 0, which leaves only the cross product squared. But here's the difference now. This is now a matrix, not a vector. Because it's a matrix, we use matrix operators, not vector operators. And with a vector operator, if you take x cross y and you put it into the equation, it comes out with the matrix this. If you square this, you get this, which is -1. And there's two solutions, not one. Okay, so the proof here is that there's no, forgetting which algebra you're in. Forgetting which algebra you're in. Okay, you cannot take the square root of -1. There is no way to represent it. It's imaginary. The only way to represent it is with the same thing. Basically saying, well, the sound of one hand clapping is the sound of one hand clapping. There is no representation using a scalar or even a vector that represent the square root of -1. However, if you have a matrix, scalar matrix of -1, again, forgetting what algebra you're using, there is a solution to the square root of a scalar matrix of -1, which is in fact the rotation matrix that we come up with Vortrix algebra. Vortrix algebra comes up with this completely on its own. I didn't go from here to there and made more Vortrix algebra do this. Vortrix algebra got there under its own power. And Vortrix algebra showed that there's actually two solutions. So, if the only way you can take the square root of a -1 is with a matrix, then logically the product of two vectors has to be a matrix if your vector products have to yield rotation. And since rotation is the name of the game, the purpose of the complex operator and pseudoscalar is to provide a 90-degree rotation operator. The matrices are real vector rotation operators. All this other stuff is false. It's pseudo. They even call it a pseudo-scalar because no scalar exists that will give you that kind of rotation. Only a matrix can give you that kind of rotation. And so any algebra that does not yield a matrix as a solution for the product of two vectors is gibberish. And I will not use it because that's the wrong answer. And when you look at the derivation of Vortrix algebra, you will see, using very simple math, that the answer arranges itself as a matrix automatically. It's wonderful. I didn't reverse engineer this to make Vortrix algebra do this. Vortrix algebra came to this conclusion of its own accord. And so I have good confidence that is correct. And all this proof is what I've just gone over. Okay, again, bottom line, a vector algebra that does not produce a matrix as part of a vector product is incomplete. It doesn't mean you can't use it. It doesn't mean it's wrong. I'm not using it because it's not complete enough for me. Okay, a vector algebra that can produce rotation without a matrix is gibberish, fraud, alchemy, imaginary bullshit. But, we've been using the imaginary for decades now, and all that geometric algebra did was suck in complex numbers to provide the same functionality. So if you're comfortable using it, go right ahead. It will not be on my dinner table, trust me. Okay, I don't care how much mathematicians or anyone else whines or complains. They're all just retarded monkeys, as I am. Okay, the only thing that matters to me is what Mother Nature says. In other words, the solution that Vortrix algebra gives for the matrix. Okay, there's two separate, you've got to separate the nuance here. A matrix is the proper solution. Is the Vortrix algebra matrix the correct matrix? That's the next question. The only person that can tell me is if it's the right or not the right one is going to be Mother Nature. Not a mathematician, not a physicist, not a cat, not a dog. So our next job going forward, and that's why we're not completing the paper yet. Okay, no sense completing the paper. What we have to do now is try to run some experiments to see if nature, in fact, yields that variation of the matrix. Because as I said in the paper, you saw the red ink there, the matrix didn't come out as I expected it to. Okay, I didn't try to force it to be one way or the other. I let it come out the way it came out. And it does something a little weird in 3D. 2D, it works perfectly fine, just as I expected. 3D, it's a little weird. I have no indicator that it's wrong. All the identities work out properly. But again, correct answers prove nothing. The only thing that matters is Mother Nature. Does the Vortrix algebra mimic what electromagnetic physics does? That's what's important to me. If not, we go back to the drawing board. Okay, and this is what I just said. So, again, if Vortrix algebra may only be a step in the right direction, we will use it to ask Mother Nature questions to develop experiments. We will continue to use it only as long as it's consistent with answers, the experimental results. Again, this is a painting that is in my possession. It's a copy of a Picasso done by an art student in the 50s. I inherited it from my grandparents. This is my effigy of Mother Nature. Okay, very stately woman, regal almost. So that's the girl I'm looking for. Okay, she gets to decide if Vortrix algebra is right or wrong, not anybody else, not any other retarded monkey. And if it diverges, we go back to the drawing board. So in the next video, we're going to demonstrate the exquisitely simple derivation of the Vortrix product using simple arithmetic. So simple, even a mathematician will be able to follow it. But this video will be for patrons only. If for non-patrons, the Vortrix algebra paper will be made public on the Patreon site on or about 20 May of this year. So you can download, but then you got to go through the trouble reading it yourself. It's gone through a review of the Patreon members. It's not finished. I don't expect to finish it until we verify that the 3D matrix is consistent with Mother Nature. No sense completing anything else until that's done. I do not want to go down on a fairy tale of mathematics without knowing that this is going to be useful for our work, our purposes, our mission. Okay, so again, no more voodoo physics or imaginary math. Thank you very much for putting up with this topic again. We will no longer discuss geometric algebra. If people put comments about it, I don't care. Oh, no, that's not true. If you can show me, going forward, if you can show me a derivation using geometric algebra that predicts something in science, using new electromagnetism or something I'm working on so you can relate it to my work, I would take a look at that. But I would rather take that from a Patreon subscriber rather than just somebody off the YouTube channel. So I have to limit. I've got so much to do in so little time. I have to be very careful about spending time looking at stuff. Okay. Thank you very much.